train score equal to 2. Number of jobs, you read that I already explained here. Cross-validation we discussed. So a few hyperparameters here, there we will try to understand, friends. By default, it is false. Okay. False means the cross-validation results when you use this attribute. When you use this, all the results, cross-validation results will show up. But if false, this attribute will not include the training scores. Because when you're building a model, you split the data into training and test, build your model on training, test on test. You get the test results. But you also should fit your model on the training data and then get the training accuracies, right? So by default, those training accuracy values won't be stored. But if you say return underscore train underscore score equal to true, the training scores also will be stored. And what scores you want? Accuracy values. Each time you're given an option, go like this. Okay. Try to see, explore. You might have questions such as, okay, what are the other scoring methods which are available? Okay, scoring. So all the details are available here. Just strategy to evaluate the performance of cross-validation, right? And you'll have the different details here. And when you scroll down, you'll have the other details also pertaining to scoring. It's not just accuracy. You can also have mean squared error, negative mean squared error, so on and so forth. You can go through that. You'll find it. Okay. So we are taking these, whatever hyperparameters are mentioned within these brackets and whatever values you are mentioning, those values will be chosen for these hyperparameters. Whatever are the other hyperparameters which are not listing here, all those will also be selected, but the default values of those will be selected. Now, when you want to fit your model, obviously you need training data inputs and training data output. So you train your model. It's taking a while, the red symbol here. The reason being all these experiments should be performed. And then when you use this attribute, this is called as attribute, then it will show you on what are the bunch of best hyperparameters. So it's giving for depth equal to 4, maximum features equal to square root, minimum samples leaf equal to 20. For this, it is giving you the best result. Best accuracy is obtained for this. Okay. So you're saying take the best estimator, means the best model, store it in this. Then go import from scikit-learn metrics, accuracy score and confusion matrix. Then compare the test data actual values and use this best model out of all the combinations out of all the combinations, you pick the best model here. Use that and predict on the test data. When you predict, you're using the best model, friends, and storing it here. And you're saying, let me use this best model and predict on the test data. What would you get? Predicted values. Then you're trying to compare it with the actual values. Here also you're doing the same thing. Predict using the best model on the test data inputs. You get the predicted values. Compare it with the actual values. You get the accuracy score. Okay. So you have the accuracy. Okay, this plus this divided by overall, it is 0.74. But this is what accuracy, test accuracy. Now we also have to calculate for training, right? So I'm saying use the best model, predict on the training data inputs, you get predicted values, compare it with the actual values. You get the confusion matrix. This diagonal, which is 4, 32, and 74 are the correct predictions. Off diagonal are incorrect predictions. And here the accuracy is 0.72. Is the training accuracy and test accuracy close to each other? Yes, that's called as a right fit model. Okay. Now, there is also something called as randomized search. And one is grid search. In grid search, what your model will do is it will try out all the combinations. Minimum samples 1, maximum depth 2, square root. 1, 4 square root, 1, 6 square root, 1, 8 square root, 1, 10 square root. Then 5, 2 square root, 5, 4 square root, 5, 6, 5, 8, 5, 10. Then 10, 2, 10, 4, 10, 6, 10, 8, 10, 10. Then 22, 24, right? 26, 28, 20, 10. It does all the experiments. It will not leave out even a single experiment, but that would be time consuming. Whereas in randomized search, it will randomly choose a few experiments and it will run. It will not run everything. So grid search will be time consuming because it will try out all the combinations and it will pick up the best results from that. Though it is time consuming, you'll get the best result. But randomized search, what will it do? It will randomly pick a few experiments and run it. So it'll be fast. It will be fast because it'll be only randomly choosing a few. But how about accuracy? Accuracy will be less. So you're saying, I want to generate a list of 1 until 50, all the values and do all those experiments for minimum samples. Maximum depth from 2 until 20, I want all the experiments and it has to be. So that's how you're defining your parameters and you want all these to be run for how many times? 50 times. Because each time you run, okay, I can also show you this. Would it show up here? Here it is, number. Number of parameter settings that are sampled. Okay, number of iteration traits of runtime versus quality of the solution. Default is 10. Okay, number of parameter settings that are sampled. Okay. So I think my explanation was wrong. I'll just take it back. So here what it does is out of all the combinations, all the various combinations, it's going to pick up how many combinations? 50 combinations randomly and it will run it. So we run the model. And once you run the model, what are we doing? We are not running the model. We are storing all these hyperparameters in this. Only when you say dot fit, it's going to run the model. And you want to fit it on inputs and output. Then you're saying, after the experiment is done, show me the best result. Where are you obtaining the best results? When minimum samples is 16, maximum features is square root, and maximum depth equal to 19. You're also saying, take the best estimator, best result model, store it in this, and use that model, best model, to predict on the test data. Then you get the predicted values. You're saying compare the actual values with the predicted values. Okay. This is one way of creating your confusion matrix. Then when you say how many times the predicted values are equal to actual values, on an average, you're getting 0.71. Then you're using your best model. You're saying, let me predict on the training data inputs as well. I get the predicted values here. Let me compare the actual values and predicted values. Row names and column names are given. Let me run it. This gives me cross table. Then If I compare the predicted and actual values, how many times on an average we have the good results? 73%. 73 and 71 are more or less close to each other. So you conclude that it's a right fit. Can I improve the accuracy? Sure, experiment. There are various other hyperparameters. Keep doing that. And at some point, you'll find that both your training and test accuracies are together increasing. Okay. All right. This is when your output variable is categorical. What if the output variable is numeric in nature? This is also a pretty straightforward code. So let me run this. Okay, whenever you're done, please remove because it will free up your memory. Import all the required libraries. Code modularity is very important. Loading all the libraries, do it at one place. Then load the data set, do the pre-processing at one place. Then splitting the data at one place, then building the models at another place, testing your model. In that way, you differentiate the code. That's called as code modularity. Whenever you appear for interviews, in the first round, it will be verbal. Second round, they will give you a data set mostly. They'll ask you to write the code. They'll give you 24 hours, 48 hours. Right? When you write the code, they also look at whether you're writing comments for the lines of code or not. Point number one. Point number two, whether you're maintaining code modularity on blocks of code. So please bear in mind that code modularity has to be included. You can, absolutely. So if your output variable is numeric, can I convert that output variable into categorical data? And then can I still apply decision tree classifier? Yes, you can. Absolutely, you can do it. So let me take this movies data set. Run it, reapply. So we have 18 columns, and you also have information on how many rows we have, how many columns we have. Do you have any missing values? No, there are no missing values. How many of these are float? How many of these are integers? How many of these are objects? How much memory is it consuming overall? All this information is obtained. Then you have df.head, which shows you the first 5 rows. Okay. And if you feel that there are certain variables and I want to create dummy variables, pd.getDummies from this df, I'm going to choose 2 columns. One is this 3D available. Another is genre. These two seem to be non-numeric. So when I say drop first equal to true, what it does is it's going to take yes and no. Out of this yes and no, which one will be 0 and which one will be 1? No will be 0, yes will be 1. Alphabetically A, B, C, D, E, F, G, H, N will come first, then 1. 0 and 1. Whatever is 0, that will be dropped. Dropped first. Whatever comes first, drop it. That's the meaning of this. Okay. Done. So if you look at this, you have 3D. In 3D, you have yes and a no. Out of that, this only yes is there. No is not there. So that's the meaning of drop first equal to true. All right. Now again, you can say info. You can see the data. And the 0, 1 are called as unsigned integers. There's no sign, plus, minus, nothing. Okay. Next, we are segregating all the inputs from outputs. So here in this data set, the business problem that we are trying to solve is, given the marketing expense, given the expense of production of the movie, right? Given the budget, multiplex coverage, so on and so forth, what will be the box office collection? How much money will the movie make? This collection is your output. So what we are saying is, take all the rows, take all the columns which are not equal to collection. Means except for collection, take all the other columns, put it in predictors. Take only collection and put it in target. Predictors are inputs, target is your output. We're just segregating these two. You can also check the type, which is not needed ideally. Says that it's a data frame. Now, what we are doing is we are splitting the data. We are importing train test split. And we're saying, let me split both inputs and output. 20% test, another 80% train. When you say random state equal to 0, what does it do? Each time you split the data, the same data will go into training and the same data will go into test. Okay, that's the application of this random state. Okay. Now we are importing tree. From tree, we are trying to import decision tree classifier, in which we are just giving maximum depth equal to 3. And we're saying, let me fit the model. Once you build your model on training, you need to predict your model on the test data. We're also predicting a model on the training data inputs. So you get test data and train data predicted values. And then here you're saying, let me import mean squared error and R squared value. Both of these we will learn later. What is mean squared error, R squared? Both of these we will learn later. Then you're saying mean squared error of test data, out actual values, and test data predicted values. You get the mean squared error. Then R squared value. R squared value ranges from 0 to 1. If it is closer to 1, it is better. That is all you need to understand at this point of time. Then you are also calculating the mean squared error by taking actual values and predicted values of training data. R squared value is 0.8. Train, test. There is a difference, 20% difference. So certainly what is happening? Is your model getting overfit or underfit? What is happening? Overfitting or underfitting? Overfitting. Training is more, test is less, overfitting. Since it is overfitting, let us try out another thing, which is pruning. Right? I would say minimum samples equal to 3, minimum sample split. That's the hyperparameter that we're using here. And I'm storing the hyperparameter in this, and I'm using that to fit the model. Once you fit the model, you're saying, let me use that model and predict on the test data inputs and training data inputs. So both test and train predicted values would be there. Then what am I doing? I'm saying, let me calculate mean squared error by giving the actual and predicted values. And also let me calculate R squared. Mean squared error doesn't make sense here, but anyways, I'll get it removed later. Then you're trying the same thing on your test on the training data as well. So you're getting 0.9 and 0.63. Is your model overfitting? Very clearly it is overfitting. Then if I say minimum samples underscore leaf equal to 3, then same thing. We are building the model. See, we are storing the hyperparameters in this. Dot fit means it will fit or train the model. And then dot predict means it's going to predict based on the train model. Then once again, you can calculate the mean squared error or R squared value. Oops. Here also it is overly overfitting. Since it is still overfitting, what are you expected to perform? You are expected to go to your grid search technique, use all these kind of combinations, and then experiment a few more options and see for what options your model is giving you good accuracy with respect to train and test, which are close to each other. Okay. What? Yeah. No problem. Sorry? Rule-based model. Oh yeah, you can see all the rules. Yeah, you can see all the rules. All the rules will come out. But if you have more inputs, it will have multiple branches. Taking each rule and then putting it in some code doesn't make sense. Ideally, what people do is they save the model in a format called as .pkl or .yaml, or there are different formats in which you can save your model, or JSON format, etc. Once you save the model in that format, you give that file to your web developer. Your web developer will put that in the code. And then what happens is whenever you have inputs, automatically predictions happen and results will be seen on your web application or mobile application. That is what. Yeah, correct. All the rules are there. You can also view all the rules, but it will just make the screen very clumsy. All the rules will be. You can see the tree also, root node, how it is splitting, all that visualizations. Exactly. Output. Exactly. Or simply put this function, dot predict, whichever is the best model, right, that you build will contain all the rules. This model that you build will contain all those rules. You just say dot predict and whatever is the new data, supply it here. No, it won't come up like that. So all rules are equally important. Yeah, all rules are equally important, but the variables that you use can be based on your information gain. You might want to shortlist only the most important rules, most important variables. You calculate information gain. Information gain can be calculated for all the variables. Out of that, you might say that, you know what, I want to take only the best 80% of the variables. And using those 80%, you build your decision tree. Every rule on a branch will have variables which will have same information gain. Root node, then the next. Okay, let me show you this. No. Rule will not have because, okay, here tell me, which rule do you think is important? But I also want to know rational. And why do you think certain rule is important? Yeah. This has the highest highest information gain. But this is highest information gain in every classification rule. Either pick up this classification rule, this is there, or pick up this is there. And in the next, you'll have the next best variable with the next best information gain. That would be there in this rule also. It be there in this rule also. You cannot say that this rule is important. How? The variables that you're using are the same. Here also you're using the same variables. Here also you're using the same variables. That means it is biased. You're saying that my rule should be biased towards these three. And this rule, I don't want it to work well. If this rule doesn't work well, you're saying your model is being biased towards credit rating. If credit rating is given, your model will give you less result. That is not how your model should work. It should be generalized. Your model should generically apply onto the future data by, saying that probably this rule should behave in a different manner, give me less accuracy as opposed to this rule. You're yourself saying that I didn't build a good model. My model won't generalize. My model is very biased, is what you're saying. That's not how it works. Your entire data is important. Yeah. 1,000 rows. It will fit. Yeah, it should. Oh, yeah. Some rule will be lengthy. A few rules will be shorter. Correct. Tell me out of the data set, entire data set, which data set will not contain the root node? Or which row doesn't contain the root node? Out of all the rows, which row doesn't contain the root node? I'll give you data set. Data set will contain multiple columns and 1,000 rows. Give me one row which will not contain this variable called student. Or name me one row which will not contain income. Every row will contain student. Every row will contain income. So every row will be involved. Okay, so we will take a break, and when we come back, we are going to talk about ensemble techniques. Okay, before that, what do you think is a disadvantage of decision tree? No, not really. Overfitting depends on your underlying data. A lot of iterations, okay. Each time I split the data into training and test randomly, will it give me the same result? No. Results will vary. Accuracy values will vary. Hence, let's look at how to fix that issue first using ensemble techniques. Okay, and then we'll proceed. Okay, let's take a break and come back. Okay, I think Madhuri has a question. Yeah, Madhuri.
So we are using pruning techniques and also the grid search CV and randomized search CV. All these techniques are used to overcome the overfitting, right?
Grid search cross-validation and randomized search cross-validation is only used to experiment with the hyperparameters, because manually giving all these options one after another and running would be time consuming, right? And the code also will have too many lines. Hence, we are using all the hyperparameter values and experimenting at one go. For that, you use grid search cross-validation or randomized search cross-validation. However, pruning techniques, pre-pruning or post-pruning, maximum depth or minimum sample leaves, so on and so forth, are your hyperparameters which are used to avoid overfitting.
So first we can do pruning techniques, and with the pruning techniques, if we overcome the overfitting, then we don't need to go for the grid search or randomized search because it is time consuming.
No, grid search and randomized search is used to experiment with the hyperparameters, Madhuri. Say your model is overfitting, what would you do?
We'll experiment with the hyperparameters. Yeah.
What are your hyperparameters?
Maximum depth, minimum sample split.
How many will you experiment? I will say maximum depth 2, run one algorithm. Maximum depth equal to 3, run one algorithm. Maximum depth equal to 3, run third algorithm. Maximum depth equal to 4, run another algorithm. Maximum depth equal to 5, run another algorithm. Are you saying I'm going to run this code? If I want you to run maximum depth from 1 to 50, are you going to run this line of code 50 times?
No.
Is that not a good? That's what you're saying. Let me do that. What I'm saying is maximum depth will help you avoid overfitting.
Yes.
Instead of saying I'll run one like this, again I'm going to put piece of code here. Okay. This time I will say maximum depth equal to 4. Again, I'll run it. Again, I'm going to fit my model. Again, I'm going to predict. I'm going to do all these things for all the options multiple times because you want to avoid overfitting, right?
Yes, yes.
But
Yes.
is this a wise decision or combining everything at one go and saying that from 2 to 20, experiment all the options at one go? Is this a good option?
Yeah, grid search CV is a good option.
Grid search or randomized search cross validation is only a mechanism to experiment with all your hyperparameters at one go.
And also we are finding the good model with the hyperparameter. Yeah. So here pruning is, I think it is not necessary every time, I think.
Maximum depth, when I use this, is it not pruning the data set?
Yeah, it is pruning. It is pruning.
That's it.
Yes,
How are
yes.
you pruning? Manually, if you want to run one by one, do it. Or
Okay.
automate it. This grid
Yes.
search and cross randomized search is automating the process. Automatically, it's doing all these experiments for you.
Okay. Yes.
Mhm.
Thank you, sir.
Okay. Sure.